Ground-based surveys. Here we have the problem of, generally speaking, quite expensive surveys where you have to be in the field with equipment there surveying data, which means that you need access to every point that you wish to survey, which in itself is not always possible. It might be difficult to reach every single point of interest. It might be dangerous, but you are capable in the field of making informed decisions. What's important to measure? This is particularly good for creating tins, where we can apply our knowledge when in the field to gather data where it's most needed and not bother gathering data where we have a surface that is unchanging, or at least changing very linearly. We can also gather other types of information where we're in the field to help inform other aspects of our study, but also perhaps even our DEM, adding this extra knowledge perhaps. But it is expensive, and we also need to be able to locate ourselves in the field. This is less of a problem nowadays with GNSS, so that we can position ourselves relatively accurately. Even if we're using a total station, we can position that with GNSS, or perhaps just perform our survey entirely using GNSS. Not always possible. We do have shadowing from terrain and maybe heavy vegetation cover that stops accurate surveys, slows them down. But this is a method that is still used, still valid, perhaps not as much as previously. Perhaps the main time this was performed, this sort of survey for gathering large-scale data, was maybe sort of the 80s to the early 2000s, and then laser scanning began to take over more and more. It is still performed. Photogrammetry prior to this was perhaps the primary source of DEM data, where we would fly over in an aeroplane with cameras and take pictures of the ground. This is the standard data acquisition, with its inherent problems. It's weather dependent. We need to be able to see the ground, so we need cloud-free skies. The vegetation cover cannot be too dense, because then we're not going to see the ground, the thing we're interested in. If we're creating a digital surface model, perhaps, of treetops, that will be a different thing. But we also need to gather enough data, enough images, so that we can use the parallax effect in order to be able to create our terrain model. We're looking at the shift in perspective, or the relative position of identifiable features, so that we can see that shift from one perspective from one image to another, and then using that shift to calculate the apparent elevation of that point. Which means that if we have smooth surfaces, snow-covered surfaces, we may have difficulty in identifying features that we can in two images, so that we can work out an elevation from them. So typically for glaciology, around the ablation area, we can gather enough data, and it works quite well. But in the accumulation area, things may fail because it's covered in snow. It's also another reason why we can't do surveys of the landscape in general in the winter in snow-covered regions, because the snow cover not only will affect the actual elevation. We won't be measuring the true elevation. We'll have the depth of the snow itself, but we won't even really be able to measure any elevation at all, because we won't be able to see things. So this is one of the problems. We also have the identifying the true support and the spatial resolution in these becomes quite difficult, because we have it in irregular cover, because we're so dependent on being able to identify features. Some areas may have a better coverage than others. So one particular spatial resolution we generally speaking don't have. That's quite an issue. And then we have this further requirement in locating these images. Where are they in the world? So we need ground control points, things that we can identify in the image, that we can measure with high accuracy using GPS or a total station, what have you, so that we know where the image is and locate the different parts of it. So that also requires going out to the field, being in place to gather data, or used to at least. And then we come to satellite surveys. For example, radar. So we have radar measurements from satellites will have a very high resolution when looking at the Z component, the elevation itself. But the support for this measurement can be quite large, and so you're missing small-scale details. It's the measurement of the average elevation within a very large support is good. It's a very high resolution, but it's only representative of the area as a whole, doesn't capture the small-scale changes within that support. So if that footprint, that support is too large for your purposes, then that's not terribly helpful. But things like, for example, synthetic aperture radar, SAR, there we can actually measure quite small areas. We can measure changes quite well. Absolute measurements are difficult, perhaps, but changes in elevation can be measured with a good deal of accuracy and precision. We also have laser altimetry, which would potentially give us a smaller support, therefore a more detailed DEM, but we have the risk of the lasers need to be able to penetrate the atmospheres, and we have atmospheric disturbances. Bad weather then also comes into it. The big advantage with radar is it's weather independent. It can see through the clouds. It's not particularly affected by these things, or we can at least compensate for them. Whereas laser is very much more dependent on the weather conditions, the atmospheric conditions below it. And then we have laser scanning from the ground, ground-based laser scanning, or at least near ground-based, from aircraft or from a tripod standing on high ground surveying. And this is perhaps the favoured method nowadays for high accuracy, detailed DEM data. In fact, it creates such detailed surveys that this in itself becomes a problem, that we have a huge number of points in these point clouds, and there's too much data. They need to be filtered. So in the end, we actually have to do a lot of manual data filtering and finding out what it is we're actually interested in. There are automated methods for this, obviously, in most simple cases, or standard cases, we can say. So it's not as big a problem, but we do need to filter the data, because what we're gathering from the field is just too much. That's the sort of problem that's nice to have. It's a good idea. This is why the laser scanning is a method is now dominant and so popular. So we could say this is a sort of ideal